So in the last video we finished up chapter 8. Now we're going to jump ahead a little bit and move on to chapter 12. We'll come back to do chapter 9. The chapters we're skipping in between, those typically come up in the second semester class. So in chapter 12 we're going to start to talk about some radical reactions, and that means things involving the movement of single electrons. So it's going to be pretty different from what we've been talking about so far. So when we think about what can happen in a chemical bond, we can have homolytic bond cleavage, which would mean if I have two groups attached by a bond, that one electron goes with one group, one electron goes with the other, and then we'd get two species with unpaired electrons, and those would be radicals. Well, we really haven't seen much of that, right? We've mostly been seeing heterolytic bond cleavage, where it breaks unevenly to form a cation and an anion. So then if we had A attached to B, and let's just say A is less electronegative than B, so we'd say partial positive on A, partial negative on B, then that bond will break with our traditional double-headed arrow, and that'll produce A with a plus charge, B with a lone pair and a negative charge. So, oops, let me fix that. That's what we've been doing, right? That's what we've been observing in our ionic reactions, like in the alkene addition or nucleophilic aromatic substitution. But now we're going to start to look at reactions involving homolytic bond cleavage instead. So there are three different reactions that we're going to look at in this section, and the first one we're going to talk about is going to be the direct halogenation of alkanes. So up till now we haven't seen any direct reaction on any alkane, but we're going to see that it actually is possible to do that. And the simplest example would be taking ethane, reacting it with, let's say, chlorine, and installing through a substitution reaction one chlorine in place of one of the hydrogens. So we'd go from ethane to chloroethane. So that's probably the first logical reaction to think about here. And like I said, an important part is it's the first time we're seeing anything happen directly to an alkane. We've seen alkene and alkyne reactions, but not alkane reactions, so that's what's particularly different. Whenever we think about a radical reaction, it's going to be formulated a lot differently in terms of the mechanism. So what we're going to see is there's going to be some sort of initiation step or steps where we form our initial radical or radicals to get us going down a radical reaction pathway. Then from there, we'll have propagation steps. And there's almost always two propagation steps. That's really the meat of the reaction. Once we get our first radical to form, how do the radicals get involved in the actual reaction mechanism? And then the last thing that we'll see is some sort of termination step where we quench our radical to end that radical pathway. So ideally, once you have initiation take place, you want propagation to keep going until you run out of all of your reactant. Either that will happen, we'll use everything up, or we'll gradually have radical drop out of the pathway, and that'll stop the reaction, and that's what we call it a termination step. So I think maybe we'll talk a little bit about energetics later on in terms of breaking these bonds, but we're going to need an initial expenditure of energy to create this homolytic bond cleavage to begin with. So we'll start by looking at that. So in our reaction, like we saw above, we can start with our initiation step. And the initiation step just means that, in this case, for example, we're going to homolytically break our Cl-Cl bond. I don't know if I said this term, but these arrows, these single-headed arrows, we call them fish hook arrows. So now I'm going to start by forming these two chlorine radicals from the original Cl2 molecule. And that costs me energy to do that. Not a ton of energy, but it still requires energy. And typically that energy is input either through an ultraviolet light or through just applying heat to the reaction mixture enough to cleave this bond. So now what we've got is the ability to use these chlorine radicals to proceed in our reaction. So now we can talk about the propagation steps. And remember what I said, it's going to be broken into two steps, propagation 1, propagation 2. So in the initiation, we made some chlorine radical. In propagation 1, we're going to consume some of that radical. So let me draw this out. So here's our ethane, and then here's chlorine radical. So what's going to happen is this chlorine radical, notice again all these single-headed arrows, it's going to pull a hydrogen away from ethane in order to make HCl, but also it's going to form this ethyl radical. So now, in the first propagation step, I used the chlorine radical that I formed in the previous step. So now, when I look at this carbon center that has the radical on it, that's still going to be planar. So that's still really sp2. And we don't really have a way to know that other than to just say it's sp2. What that means is we're assuming that extra electron is sitting in an unhybridized 2p orbital rather than a hybridized sp2 orbital. And we don't know that other than by looking at the geometry and saying it's sp2, so that must be the conclusion. So then what happens in propagation step 2? Well, now I'm going to use this radical that just formed and I'm going to react it with Cl2. So not chlorine radical, but Cl2. And again, fishhook arrows, now 3 of them. And this is going to form our product. And form more chlorine radical. Oops, let's use a different color there. So right away in this reaction, we see make chlorine radical, use chlorine radical, make more chlorine radical. And that should make sense as you think about the 2 propagation steps. those need to be sustainable. We enter into that cycle once we've made one chlorine radical, but then we want those steps to keep repeating until all the reactant gets converted into product. And that is what will happen unless our termination step occurs. And the termination step is really anything in which the radical gets quenched. So the simplest termination step to think about is if two chlorine radicals end up reacting with each other to regenerate Cl2. If that happens, then we're no longer going to have radical present to react with. In that termination section, I proposed two other possible termination steps. One where our ethyl radical happens to react with a chlorine radical, and that looks good, right? I'm making product, but I'm making product at the cost of losing my radical species, so that's going to shut down the pathway. But certainly that's one possible termination step. So when we're thinking about termination, it's anything that's getting radicals to drop out of the process. So now we've shown as one possible termination the two chlorines reacting together. Then we've seen the ethyl radical and the chlorine radical together. So then naturally the last possibility for a termination step would just be two of the ethyl radicals, and I'm just going to face them toward each other to make it easier, reacting together to technically make butane, right, when we see this through. So 1, 2, and then I just drew butane as a line angle structure, 2, 3, 4. And if we want a number, just to be clear, 1, 2, 3, 4, 1, 2, 3, 4. So that's what's going on with the radical type reaction. And we can certainly do this with chlorine and bromine. Again, it doesn't work well with fluorine. I think it also doesn't really work well with iodine because of energetics. So those are really the two that we're looking at. So the next thing that I want to talk about with regard to this type of reaction is the selectivity of the reaction. And when I say selectivity, I mean using Cl2 versus Br2, how do the results differ? So surprisingly, it does make a difference. If we use bromine, and let's say we have propane as our reactant, we'd say react it with bromine, and then a light source, so usually a UV lamp is shining on it. We'll almost exclusively make 2 bromopropane. So make the secondary alkyl halide. But on the other hand, if I use chlorine, same reaction with propane, but if I use chlorine instead, I'm going to actually make substantial amounts. It's almost a 1-to-1 mixture of 2 chloropropane and 1 chloropropane. So now we're seeing both the secondary alkyl halide and the primary alkyl halide. So something unique is happening based on whether I react with chlorine or bromine, and that'll take some substantially deeper analysis to get to, and then that's what we'll do next. I'm going to switch over to some slides that we'll go through that'll help us understand something called Hammond's postulate, or the Hammond postulate, and that'll explain why chlorine is not selective but bromine is selective. So before we get into that, just have that idea in mind, right? If my goal is to only add the halogen to the more substituted carbon, then I would do that with bromine. If that's not my goal, then I would do it with chlorine. And while we're here, let me add one other piece of information, we'd rather use chlorine, right? It's easier to work with, it's less wasteful. So then you'd say, well, when would be a good time to use chlorine? Maybe something like cycloalkanes, where I just want to add a halogen somewhere, because I know that selectivity is not important, right? If all of my carbons are secondary carbons, that would be a great time to use chlorine rather than anything else. So it's not like chlorine is not useful because of its lack of selectivity. We can still find times where either we're not seeking that selectivity or we're using a reactant where selectivity isn't all that important. So it should be a big deal to look at this and see, hey, bromine is only going to the secondary carbon, chlorine is going to both, and that's what we want to try to get to. So let me switch to these slides so we can kind of talk our way through that. Okay, so I had kind of a larger set of slides about radical reactions, and I just picked a few to talk about. I think the handout that I gave you really covers everything in more detail. So our first point, right, we said regioselectivity is high for bromination, but it's not as high for chlorination. And so showing exactly the same two examples, right? Propane with bromine, we see that it's 92% 2-bromopropane with only 8% 1-bromopropane. That's particularly interesting, right? Because there are 2 secondary hydrogens, but there are 6 primary hydrogens. So it's a substantial selectivity for adding to the secondary carbon. Like that, some amount of the primary product is made. Then we see down below, if we do the same thing with propane, we'll see it's 5743 2-chloropropane to 1-chloropropane. So really that's telling me that it's selective for the primary position, right? So again, we'd say there's 6 on the outside and only 2 on the inside, but now it's telling me the amounts are relatively close. So that means somehow in chlorine we end up selecting for the outer position, which is particularly unique. So the best way for us to talk about that idea is to think about something called Hammond's postulate. And so the postulate itself is a pretty simple statement, but we can carry it pretty far in terms of our interpretation. So Hammond's postulate is primarily interested in talking about the structure of the transition state as a function of the energetics of the reaction. So first it talks about an exothermic reaction. And so, right, if it were exothermic, we just say that product is lower in energy than reactant. And it says for an exothermic step, okay, the structure of the transition state for an exothermic step is reached relatively early in the reaction and resembles the reactant more than the products. And so really what this is saying, and we'll elaborate on this on the next slide, is if the reaction is exothermic, the energetics of reactant and transition state are going to be closer together than the energetics of product and transition state. So then it comes back to the other side of this to talk about what's going to happen in an endothermic step. And so now it's saying the structure of the transition state for an endothermic step is reached relatively late, and the early and late is talking about which one it looks more like energetically, relatively late in the reaction and resembles the products of that step. So same small picture, and we'll draw this bigger on the next one. If here's reactant, transition state, product, now we'd say, well, if here's reactant and here's product, the transition state is going to be more similar to the product than the reactant because they're closer together in energy. So the last point here, it says this postulate applies equally well to the transition state for one-step reactions and to each transition state in a multi-step reaction. So regardless of whether this is the only step in the process or one of many steps in the process, we can make the same generalization. So we can look at that a bit bigger than what I just drew in the corners over there. We kind of have an exaggerated case here. The labels are down below, but I'll put them up here too. So here's exothermic, and then here's endothermic. So this kind of helps us look at the early late terminology that we use. So you can see here reactants are higher in energy, so the transition state happens pretty soon into the reaction. Whereas in the other case, we say here are products, the transition state is closer in energy to the products. So now we see that that is achieved later in the process. So the big jump in logic that makes Hammond's postulate so powerful is it says if whichever structure the transition state is closer to in energy, it also looks more like that structure in terms of its actual three-dimensional construction. So that's the next big step, is to say exothermic, the transition state looks like the reactant, and endothermic, the transition state looks like the product. So now we want to use that and apply it specifically to our reaction. So the example here, it looks like it's thinking about a slightly more extreme example where we're thinking about 2-methylpropane as our reactant. And so if we're thinking about for chlorination, we'd expect that we would get chlorine both in the interior position and then on the end position as well. So let's see what we're looking at here. So now it's asking us to consider those possibilities for chlorine and bromine. So the step we're interested in is where the halogen radical pulls off the hydrogen from the hydrocarbon to make the carbon-based radical. So that's what we're looking at here, right? It's saying compare the two radicals that could form in our reactions, whether we use it with chlorine or with bromine. So it turns out the overall energetics when chlorine is involved, we end up with an exothermic process. Just for this one step of chlorine pulling a hydrogen off, and for bromine, the same step ends up costing us energy. It ends up being endothermic. And you can see these energies are listed here for each one. And so what's different here really is whether I'm forming HBr or I'm forming HCl. The rest of it's the same, right, in terms of what we're observing, but because we have to think about the overall picture of this reaction, the result is the chlorine radical removing the hydrogen is an exothermic step regardless of where it occurs, and the bromine radical removing a hydrogen is endothermic regardless of where it occurs. Okay, so the next two slides kind of say what I just said, but let's read through them together to try to make sense of it. Because hydrogen abstraction for chlorination is exothermic, the transition state resembles the alkane and a chlorine atom. Those are the reactants. And there is little radical character on the carbon in the transition state because it doesn't look like the products. Since the transition state looks more like the reactants than the products, the conclusion is that the regioselectivity is only slightly influenced by the radical stability trend. Since the transition state for chlorination isn't very radical-like, the radical stability trend favoring the radical forming on the more substituted carbon has less of an impact on the reaction. So the result is that when we take propane and react it with chlorine, there isn't a drastic difference in the likelihood of adding chlorine to the inside position on carbon 2 versus the outside position on carbon 1, because the radical stability trend doesn't impact the reaction very much since the transition state isn't very radical-like. So pretty advanced stuff in terms of what we typically talk about in organic chemistry, but I think it's a really good example to think about how complicated organic chemistry really is and how the energetics of things becomes involved. So the next slide basically says the opposite, right? It says because hydrogen abstraction for bromination is endothermic, the transition state resembles the product for that step, and the products for that step include the radical. And so since it looks more like the product than the reactant, since it's endothermic, then the process is going to be influenced to a greater extent by the radical stability trend. So now we're saying reactant, transition state. Let me move my product up a little higher. Reactant, transition state, product. So now here, transition state and product are closer in energy. So it's saying since the transition state is more radical-like, regioselectivity is greatly influenced by the radical stability trend. So now when we bring in propane and react it with bromine, we're going to almost exclusively put the bromine on the more substituted carbon because the radical stability trend is a critical part of this. So lastly here, we can kind of look at the energetics of these steps just to kind of show you what's taking place. So really what it's showing you is the reactant, product, and transition state energy, so we can kind of think about how all this works. So in the first case, that reaction is mildly exothermic, so we see reactant and transition state are not that far apart in terms of their energy. But the other thing we see here is the energy gap between the forming the primary radical and forming the tertiary radical isn't all that different in terms of our energetics. And that makes sense, right? If those two pathways were substantially different in energy, then we'd see more of one than the other, but we see about equal amounts of the two because there really isn't a big energy difference between the transition states for the two pathways. On the other side of this, what we see is reactant and product, and then the transition states are closer in energy to the product energy levels, so that's what we'd call a late transition state. But now what you see, if we zoom in on that, is immediately the energy difference between the two pathways, primary or tertiary, are substantially different. So in the big picture, that should make sense, right? In the case of the exothermic chlorination, the two pathways to add primary and tertiary are pretty much the same energy-wise. So that's not going to make much of a difference, but for the endothermic bromination, those pathways are immediately way different in terms of energy, and as a result, the product distribution is going to be influenced by this a lot more. So just to remind you, right, it's talking about a slightly different reaction than our original example, where we're thinking about 2-methylpropane and talking about which of these products is going to be favored more. So Hammond's postulate is a pretty big deal in organic chemistry, and it's really the most important for these radical type reactions, but we do see it elsewhere as well. I think the last slide is about stereochemistry, and we don't need to worry about that. Remember, just in passing, that radicals are sp2 hybridized, so when we add these halogen atoms, if it happens to be adding in a place to create a chiral center, we should end up forming a racemic mixture. Okay, let me go ahead and stop there. That really takes care of what we want to say about the first of the 3 reactions under the class of radical reactions. So there's a lot to think about here, right, because it's substantially different from the reaction types we've been looking at. And with regard to Hammond's postulate, we really haven't talked about anything that's that complicated with regard to the energetics, but it's really our only way to explain the high level of selectivity in bromination and the low level of selectivity in chlorination. But yeah, let's go ahead and stop there.